Hello everyone. In this video, we are going to discuss some of the previous year PG entrance exam questions on real sequences. So these are the questions. Well, now let's see the solutions of all this. And here is the first question. And this question is simple. Limit n tends to infinity 2 to the power n plus 3 to the power n. So as n tends to infinity, it becomes 2 to the power infinity, and this one is 3 to the power infinity. Both are infinity, so sum is again infinity. So the answer is D. Question number 2. Limit n tends to infinity 1 by n times 1 plus 2 to the power 1 by 2 plus 3 to the power 1 by 3 plus etc. plus n to the power 1 by n. Actually here we cannot take the limit as n tends to infinity directly in this question. Then what happens is that the denominator becomes infinity, and the numerator again we will be getting infinitely many times. As n tends to infinity, you will get infinitely many times in the numerator, right? So that is going to be an indeterminate form. Okay, so here see, you consider this as n to the power 1 by n as an, and you take the limit of that. And we know that nth root of n as n tends to infinity, that's going to be 1. That's a standard limit. We know that, right? Now, by Cauchy's theorem, if we have an whose arithmetic means as n tends to infinity, that also converges to the same limit of a. And that's what that theorem says. So, limit n tends to infinity a1 plus a2 plus etc. plus an by n, that converges to the same limit of an, and that's equal to 1. Okay, now a1 is 1 to the power 1 by 1, and a2 is 2 to the power 1 by 2, a3 is 3 to the power 1 by 3, and so on by n is equal to 1. So the answer is just 1. So this is an application of Cauchy's theorem to find the limit. Okay, now question number 3. A sequence is given, and it's a recursive sequence. An plus 1 is equal to 2 minus 1 by n, 1 by an. Okay, so and the first term is 3 by 2. So it's given that it's convergent. So what is the limit? It's given that it is convergent, so we can assume that L is the limit of the sequence, and you substitute L here. So as n tends to infinity, it becomes like L is equal to 2 minus 1 by L, and when you solve it, you will get L square minus 2L plus 1 is equal to 0. That's L minus 1 equal to 0. So L is equal to 1. So that is one way of doing it. So the limit is going to be 1. All right. And another method is that you try to find out the nth term of the sequence directly by finding the each term. So given that a1 is 3 by 2 and a2 is 2 minus 2 by 3, and that's going to be 4 by 3, and a3 is 2 minus 3 by 4, that's going to be 5 by 4, and so on. So it's easy to verify that an is equal to n plus 2 by n plus 1. So as n tends to infinity, both numerator and denominator will be of the same degree polynomial. So it's like 1 by 1 is going to be the answer. So that is another way of doing it. Okay, so any of these methods may be applied. And see question number 4. A sequence is given, so we need to find the limit points of that. So it's like minus 1 all to the power n times 1 plus 1 by n. So let's see what happens as n tends to infinity. As n tends to infinity, 1 plus 1 by n converges to 1. Okay? But this minus 1 all to the power n is an oscillating sequence. So this value is going to be either 1 or minus 1. So 1 times 1 is 1, and minus 1 times 1 is minus 1. So these two are the possible limit points that we will get. Alright, so the answer is D. Okay. Fifth question. Which one of the following statement is wrong? The wrong statement. Okay. every convergent sequence of real is necessarily bounded, and that is a classical theorem. Every convergent sequence is bounded. So that statement is wrong. I mean, statement is right, therefore option is false. All right. Second one, every sequence of reals has a monotone subsequence. That's also a theorem. So for every sequence, we can have a monotone subsequence, either an increasing sequence or a decreasing sequence, right? And that is possible. Either an increasing sequence or a decreasing sequence, okay? Uh, so that's also possible, and the proof is also given in all the classical textbook, and that's a construction. Okay, so that is also possible. So the statement is right, option is false. Now every monotone increasing sequence which is bounded above is convergent, and that is what is monotone convergence theorem, right? Every monotone increasing sequence, and that is bounded. So definitely that converges to the supremum of the sequence, or the upper bound. The supremum of the sequence. So that's monotone convergence theorem. The statement is right. So the option is false. Now every sequence which is bounded above has a convergent subsequence. Okay, so here actually every sequence has a convergent subsequence, and I mean every sequence has a monotone subsequence. That is, statement is right as in B. But every sequence which is bounded above has a convergent subsequence, and that's a thing. So here is an example. Bounded above sequence. You consider uh, you know the sequence n is equal to minus n. All right. So you will get minus 1, something like this, and this is bounded above by 0, right? The sequence, this one has a upper bound, and that is 0, and that goes to minus infinity, right? Okay, this one does not have a convergent subsequence because every subsequence diverges to minus infinity, right? Every subsequence converges to minus infinity or diverges to minus infinity, right? So uh, this is a false statement, therefore that's answer. So D is the correct answer. See question number 6. We have two sequences an and bn, and an is 1 plus 1 by n all to the power n, and this one, it's a classical sequence, right? As limit n tends to infinity, 1 plus 1 by n all to the power n, and that's e, right? That's a standard limit, e. Similarly, limit n tends to infinity, 1 plus 1 by n to the power n plus 1. And here actually you can write this as limit n tends to infinity, 1 by 1 by n all to the power n times 1 plus 1 by n, right? And here again, the first part converges to e, and the second part converges to 1. So it's like e is the answer. So actually both these sequences converge to the same limit e. And let's see an now. An. So when n is equal to 1, you will get 2. When n is equal to 2, you will get 3 by 2 the whole square. So that's like 1.5 the whole square. It's something like 2.25 and all, 2.25. And here it's like 4 by 3 the whole cube. That's again, it's a greater quantity than 2.25. You can verify it. So we can see that, an is an increasing sequence. An is an increasing sequence. Okay, and we know the value of e, right? E is some 2.708, something like that, right? A starts from 2 and that converges to E. So that's an increasing sequence, right? From 2 that increases to 2.7, something like that. And here Bn starts with 4 and that starts decreasing, right? Because when n is equal to 1, you will get 4. When n is equal to 2, you will get 3 by 2 the whole cube. And that's going to be 27 by 8. It's like 3 point something, right? So here actually this value decreases to E, right? So an is an increasing sequence and bn is a decreasing sequence. All right, so that is our conclusion. So an increases and sequence bn decreases. All right, so the answer is one of these two sequences is monotone increasing and the other one is monotone decreasing. So C is the correct answer, all the other options. are false. Now question number 7. The sequence is not a Cauchy sequence. Okay, so Cauchy sequence implies convergence, right? All right. Therefore, if it's not Cauchy, it does not converge. Okay, it does not converge. So definitely you can say that that's not a convergent sequence. If it's not convergent, definitely that is not bounded, because every convergent sequence is bounded. All right, convergent sequence is bounded. Okay, so if it doesn't converge, it need not be bounded. So definitely we cannot say that the sequence is bounded. So that is a false statement. So one option is that it can be, if it's not Cauchy, it can be oscillating sequence, oscillating finitely, oscillating infinitely, or divergent. There are many options, and among these options the only possibility is that it can be a divergent sequence, can be oscillating as well. Okay, but in the options it's given only divergent sequence, right? So the possible option is divergent sequence. If it's not Cauchy, then it's divergent. Now question number 8. Again, a recursive definition of a sequence is given. Xn is equal to x1 minus pq by xn minus 1. And the first term is given as x1 is equal to p plus q. Okay, so we need to generalize, or we need to find the nth term of the sequence. Okay, so one option is that we use induction or something like that for finding the sequence, but actually that takes time. All right, so here what I'm going to do is I just find the second term x2. Okay, and when I put 2 here, which among these options satisfies that, that's all I'm going to check here. Okay, so x2 is equal to x1 minus pq by x1, and x1 is given as p plus q. So you take the LCM and all and you simplify, you'll get p squared plus q squared plus pq by p plus q. Okay, so when n is equal to 2, when n is equal to 2, what happens for a? So that's x2 is equal to p cube minus q cube by p square minus q square. So when you simplify, this is what you will get: p minus q times p square plus q square plus pq divided by p plus q times p minus q, and this p minus q will be cancelled, and you will get p square plus q square plus pq by p plus q. That's what we get here, right? So these two are right. These two are the same. Okay, therefore there is a chance that first one can be the option. Okay, and you can verify that in B, C, and D, when n is equal to 2, you won't get this term. All right, you won't get, because here when n is equal to 2, uh, here you will get actually p cube plus q cube, and here p square plus q square. Even a simplification is not possible, so this is not the answer. And here x2 is going to be pq the whole square by p square plus q square, and that's not the option that we have here, so that's wrong. Similarly, option D is also false. Therefore we can choose the first option as the answer. Okay, now once you fix this one, now you can use induction to generalize this one, so I'm not going to do that. Okay, well, maybe as a practice you can do that. Now see question number 9. All right, so two sequences are given, an and bn are sequence of real numbers. So a1 is 1. So an plus 1 equal to an plus minus 1 all to the power n by 2 to the power n, and this is an plus 1. So first let's find out what is an. So a1 is 1, right? a2 is a1 plus minus 1 by 2 by definition, and a1 is 1, so it's 1 minus 1 by 2. Now a3 is going to be a2 plus 1 by 2 square, so it's 1 minus 1 by 2 plus 1 by 2 square. So a4 is 1 minus 1 by 2 plus 1 by 2 square minus 1 by 2 cube. And so in general, an is going to be the sum of n terms, 1 minus 1 by 2 plus 1 by 2 square and so on, right? So what happens as n tends to infinity? So this becomes an infinite sum. So generally, that becomes a series, and that's a geometric series. Okay, that's an infinite geometric series, and actually we'll see the idea of series in the later sessions. Okay, so this is nothing but we have sigma minus 1 all to the power n by 2 to the power n. And there the common ratio is 1 by 2, which is less than 1. Therefore, that converges to a point a by 1 minus r. R is a common ratio. A is the first term. So 1 by 1 minus 1 by 2, that's going to be 2. So sequence an converges to 2. Okay, so that is what the idea. Okay, and here the sequence, actually the sequence is a sum of times is a sequence, right? So as n tends to infinity, it becomes an infinite sum, all right, and that's called a series. All right, so that sequence converges to 2. So an converges to 2, and now the definition of bn is 2 an plus 1 minus an by an. That's what the definition of bn. So just take the limit of bn, let's see what happens. So bn is this, just take the limit of this, and you will get 2 times, as an tends to 2, an plus 1 also tends to 2. So 2 times 2 is 4 minus 2 by 2, and that's going to be 1. So an converges to 2 and bn converges to 1. So that's what's answer that we have. Now let's see the options. An converges to a non-zero number and bn is a Cauchy sequence. Yeah, bn is also convergent, right? So option B is right. Okay, an does not converge to 0. An does not converge. So A and C are false. N converges to n. Pn is not a convergent sequence. Okay, so all the options A, C, D are false, and only correct option is B, because both the sequence An and Bn converge. Well, the last problem, question number 10. See, three sequences are given, An, Bn and Cn, and it's given that Bn is 8 to n and Cn is 8 to n plus 1. So what are Bn and An? So simply saying Bn and Cn are two subsequences of An, right? So Bn and Cn, that means the even indexed terms of An is Bn and the odd indexed terms of An is Cn. Okay, so we have two subsequences of An and it's given that An is convergent. So every sequence, every subsequence of a convergent sequence is again convergent, and that converges to the same limit. We have the theorem. Okay, so An converges implies both Bn and Cn converge even to the same limit of A. Okay, so yeah, C is the correct answer. All the other options are false. All right, so that's it. Now practice the tutorial problems, and yeah, that's it. So I think we can wind up the session. Thank you.